Okay, hello, hope you're doing well. We're going to start off chapter 2 with some problems covering atoms, molecules, ions. And the first one, we're classifying these given species as an element, a compound, or an ion. So we're going to look at this first one, Cl2, and this one will be, because it's only one type of atom, an element, one type of atom. We have CO3 2 minus. The important thing is going to be the charge here. So if we see a charge, this will be an ion, charged species. That's, whether it's positive or negative, it's either way it's considered an ion. So also in part C, we have a charge up here in the upper right corner of positive, meaning it's an ion. For D, we have a compound because it's composed of more than one type of atom. More than one type of atom. So that's the difference between that one and the first one we did with just two chlorines. And then here, of course, we have just one atom, so it has to be an element. So pretty basic, but essential definitions that you should know. All right, so for number 2, we're going to fill in this table. These are dealing with atomic symbols. So you could think about a symbol being, some letter or letters that represents the particular element or type of atom. Up here, you're going to have a mass number, which is sometimes called A. And this is, the number of protons plus the number of neutrons. Down here, you're going to have the Z, which is the atomic number, which is just the number of protons that determines the element. And then, of course, here you could have a charge if there is one, and that's going to be related to how many electrons there are compared to the protons in the atom. So if there is no charge, neutral, the same number of positive and negative charges. So one thing I'll point out that's also very important to remember is that protons have a positive charge, electrons have a negative charge. Neutrons, of course, are neutral, as the name stems from. So when you're balancing the charges or determining the charges of an atom, that's what's going to be important is the protons and electrons. And specifically removing or gaining electrons, which we'll get to very shortly. Okay, so oftentimes the symbol does not include the atomic number. That's because you'll have access to a periodic table like this. And if you look at carbon here, so what's different with the periodic table is that the atomic number, is the number usually written above the element. The number below it is the mass number, which is actually an average mass, which we'll get to in the next chapter. So don't really worry about that too much yet. So we want to translate that to carbon 6. So basically that again on the symbol will be in the lower left when we use the standard atomic term symbol notation. So if you want, you can throw in this 6 down here for the atomic number, and that of course is going to be the number of protons. So that's going to always match. Those should always match this number down here and this proton, right? Neutrons, an easy way is just to subtract A minus Z, or the mass minus the atomic number. So this is going to give us 6 neutrons in this case. And then how many electrons would this have? Well, if there's 6 protons, there's no charge, there must be 6 electrons. So neutral, again, means protons, electrons are the same. Okay, so moving on, hopefully that makes sense. Starting with the numbers of protons, neutrons, and electrons. And based on the number of protons, this should be atomic number 26. If we consult our table, look at then the number 26, which is again, the atomic number. This is going to represent, this is going to be for iron. So we can write Fe for iron. Fe coming from a Latin name of iron. A lot of these elements the symbols are based on old kind of historic names. So just if you're new to chemistry, you'll have to kind of memorize some of these things. All right, so, and when we have the protons and neutrons given, we can then add them up. So if we add up 26 and 30, that's going to be 56. That's the mass, right? So again, protons plus neutrons equals the mass. Okay, are we done? Well, what you want to check in this case is the number of electrons. So since the number of electrons does not match the number of protons, this is not a neutral atom, so we need to have a charge here. So we have 2 less electrons in this case. So that's going to mean that there's a +2 charge or 2 plus. You can write it either way. So this, again, because there's 26 positives, 24 negatives, we have a 2 plus charge. Okay. All right, so last one, we have Santabarbarium. Actually, it's antimony, but I like to call it that. So if we look at a table, we might have to find, this symbol. This table didn't actually copy that well. Sorry about that. But here it is down here. It's actually number 51. And this antimony, we can write 51 again if you want. So we have 51 protons. And then the neutrons, again, we can subtract the total mass minus the protons, should be 71. And then the electrons, so here the charge is 3 minus, so we have 3 extra negative charges. So in that case, we should have 3 extra electrons, or 3 more electrons than if it was neutral. So to summarize, a very important point is you always want to gain or lose electrons. This is a symbol for electrons, E minus, by the way. Not protons, because that would change the element. So you can't just make antimony negative by losing protons, and it would change it to some other element. Okay, hopefully that makes sense. Number 3, we have a question about isotopes. And this is, again, just a definition that you want to be aware of, which is the same element, but different mass. So you can also say this by saying same. What would be the same element would be the same number of what? That would be the same number of protons. If it has a different mass, it'd be a different number of what? Different number of neutrons. So you can think about it that way, or if you're given the symbols, you want the same element, so that would eliminate something like B, because those are different elements. You want different masses, so D is incorrect. These are just actually called allotropes. They're different forms of oxygen, but they're not, there's no masses given, so we can't tell. And for A, we can eliminate that because that's just a neutral nitrogen 14 and an ion here, right? But they're the same mass. So that leaves us with these two, which we have, again, both carbon, but different masses. One has 6 protons and 6 neutrons, and one has 6 protons and 8 neutrons, right? So you can also kind of write this like this. Then you can hopefully see the difference with the neutrons.